Welcome everyone to the Museo Nacional de Ciencias Naturales here in Madrid. How many of you have been here before? Most people, lots of people. Okay, so you will have seen the exhibitions in the museum. You might have been to some events organized by our fantastic communication and education department who have helped organize the event today. What you might not know is that the museum also has about 350 people working here, of which more than 200 are actually doing research on the life sciences and the earth sciences. And most of our research is actually trying to find out fundamental things about how the world works, which are then useful for us to try to tackle the enormous and some might say almost insurmountable environmental and societal problems that we're facing today. And so this presentation today, which I'm really glad to be presenting, my name's Rob Wilson, by the way. I'm the Deputy Director for Training here at the museum. So this presentation is timed to coincide with World Environment Day. And it's a great pleasure to have here giving us a presentation today David Jarvis, who's currently based at the Alfonso X University in Madrid, who was trained as an engineer and working in materials science. So these are specialities which are a bit different to most of the biologists and the geologists who work here at the museum. But the very important points that David are going to make today relate to the fact that in order to understand and tackle environmental problems, we need to bring together understanding and human experience from a whole range of fields, right across the sciences, right across the arts and culture of human history. And I think there's a lot of really interesting stuff that we're all going to find out today. So thank you very much, David, and I'll give the floor to you.
Thanks a lot. Thank you, Rob. So I need to check whether my microphone is working. Is that good? Thank you, Carlos. Yeah, thank you very much for introducing me. I'm going to say a few words about myself during the presentation, so I'll defer that. I just wanted to say that I'm dedicating this presentation to the memory of Ben Sneath, who's my best friend, who unfortunately died end of last year. And he died of Huntington's disease, which is a terrible sort of rare genetic disease. And hopefully the outcome of the Atlas of Human Imagination is to try to kind of inspire young people to get into medicine or any form of science, so that we can try to get rid of these kind of sort of genetic rare diseases, which are devastating, of course. I'd like to also thank the museum here as well. MNCN is a fantastic organisation. And it's a 250-year-old museum, I understand. It's one of the oldest in the world. And as you can see, we're in a fantastic room today. We're in the Salon de Actos. And you can see all kinds of wonderful exhibits, in some of the cabinets here, beautiful exhibit items. And one of the colleagues, I think Gemma, just mentioned that there are 11 million exhibit items in this museum, 11 million objects archived. So that's a fantastic cultural archive of our heritage. And today we're quite lucky as well with the museum have very kindly given me some props. So when I go through my presentation and I talk about different topics, whether it's to do with brain science, AI, nuclear fusion, we have all of the exhibit items that we can show. And some of them are world unique. Some of them are special and Nobel Prize winning bits of science and information. So we're in a truly unique environment today, so it's fantastic to be here. And I understand as well that we're being videoed, so we're actually being live streamed on YouTube today. So best behavior, everyone. And I'd like to thank any viewers who are watching this live now on the internet as well. Thank you for attending. Oh, sorry, yeah, Rob's just mentioned, please check on your mobile phones to turn them to off, otherwise we might get some phone calls and disruptions. I should probably do the same myself. Practice what you preach, yeah. Okay, right. So without further ado, let me start with, this is what I'm going to talk about today. I'm going to introduce myself very quickly. I am probably the least interesting part of the whole presentation, so I won't spend too long talking about me. What I want to do is talk about the poster and why, how it was developed, how it was created, how I went about developing that. And I want to mention something called cross-disciplinary thinking. To the students, do you all know what that means, cross-disciplinary? It's essentially, in school you have your certain subjects, you have like biology and chemistry and geography, art, but cross-disciplinary is when you think in a creative way and you bring it all together because it's all just knowledge. So rather than having separate silos, see it as a whole, a very holistic approach. So I'm going to say a few words about that today and why I think that's very important. And I'm going to give some examples of that. I've got 4 examples that I'm going to talk about. And they are a whole range of different topics. And it gives a bit of insight into the way I think, at least. It also to how to enter, how to be creative, how to use your imagination, because everyone's got imagination. So every single person in this room right now has got fantastic imagination, but it's all about using it and being able to use it. And then at the end, I'll wrap up with some final thoughts. And there's also going to be about 15 minutes for questions today. We're not in a big rush to get out of the room, so there'll be plenty of time. And I'm looking for some imaginative questions, especially from the students in the room. And there's also, I've brought 2 posters with me today. We have that one there and 2 more, which will be prizes. So whoever comes up with the most imaginative question today, and there's for good gender equality, there's one for the boys and girls. So as you go through as we go through the presentation today, have a think about questions and see what you can come up with. Okay, right, really quickly about me. So that's me in the lab at UAX. That's where I work in Madrid as a senior research professor. And originally I'm from a town called Chatham, which is just to the east of London in England. There you can see on the arrow there. Chatham is famous for Charles Dickens. He was also from the town of Chatham. And then after school, I did my A-levels as well, just like you. And then I went westwards. And then I went exactly due west. I went to Swansea University in Wales, which is there on that arrow. And that's where I did my engineering training. I did my bachelor's. I did a PhD there in metallurgy, the study of metals and alloys. And they made me an honorary professor around about 2012, I think. And these are the organisations I've worked for. So I haven't done a lot of job hopping. I've been quite stable. I've only had 4 employers in 25-something years. I've worked at BMW in Munich, European Space Agency. Then I set up a company called VSCA in Norway. And now we relocated last year to Madrid. And I'm working at UAX, which is one of the major universities here in Madrid. I'll say a few words about what I've actually done there. So while I was working at BMW, I was very lucky actually to be working on all kinds of automotive components for think cars like the Z3. And I worked at the European Space Agency for 15 years, inventing and discovering and working on all kinds of new projects to do with materials and energy. I started off as a research fellow and then slowly, gradually climbed the ladder and became head of new materials and energy. One of the things I worked on, and I'll show you a nice little video. You have no idea what's coming next, I don't think. This is hard to predict. But this is one of the projects I worked on, is the International Space Station. And that gave me exposure to something called microgravity research. So doing research in weightlessness. So now I've spoilt it. You can see what's happening here. And this is one of the experiences. So I think I'm around about 25 in this video. So these are special flights called parabolic flights where you are weightless, and you can do this around about 30 times per day over a whole week. So by the end of it, you're kind of like a bit sick and tired of floating around. But yeah, nonetheless, it was like probably one of the best days of my life. Absolutely fantastic experience. And the experiments we were doing on that particular flight, on that particular day, then went onto the space station, and all the astronauts were trained, so including Pedro Duca, who's the Spanish astronaut. So I've known him, and he's been trained on some of these experiments. So yeah, fantastic kind of exposure to the world of research to do with materials and space. And after that, then I decided I wanted to start up a company. So then we relocated to Norway for various kind of investor reasons. And we worked on something called nuclear fusion, developing materials. And I've got a whole slide on that, which will come a bit later on. So I'll talk about that later. And likewise, now I'm based at UAX in Villanueva de la Cañada. And again, still working on research. I've spent my whole 25-year career working on research and still going strong in an academic setting at the university. So interestingly, I've worked for big companies, small companies, startup companies. I've worked at government, intergovernmental agencies, and academia. So I've seen every kind of organization, and they all have pros and cons and various different benefits. But the key driver when you're doing research is this: imagination. If you're inventing and you're doing, think inventively, and imagination has served. Right, that's enough about me. So the Atlas of Human Imagination, which is the topic of today's discussion on World Environment Day, which Rob has already mentioned. A lot of people ask me the question, why did you even come up with this? How did you go about doing it? Just like questions of why and how. And then bizarrely, as a scientist myself, my inspiration didn't even come from science. It came from this. Does anyone know what that is? Put your hands up if you've seen that. Oh, yeah, lots of people, yeah. And if you haven't seen, oh, is the microphone on, is it? Ah, okay. Yeah, so I was on holiday with the family last August, and we were in El Prado. And I'd heard about this painting, but I'd never seen it, and I'd never really seen it up front. So for the first time in my life, I was staring at it, and it's massive. It's a triptych with these 3 panels that open and close. And it blew my mind. I just couldn't stop looking at it, and I was staring at it for at least half an hour while my wife and kids were getting bored and drifting off to some other room. I was just literally stuck in place. And it's, it's obviously has some kind of religious symbolism there as well. But what's amazing about this painting is the imagination that Hieronymus Bosch had 500 years ago. So when you actually kind of look at this from a historical perspective, this piece of art, Europe was just coming out of medieval times 500 years ago. That was kind of the end of medieval times. And here is a Dutch painter. Oh, there we are. And these are just zoomed in sections of that triptych. And it's mind-blowing. So you've got these pink castles and statues and palaces, and there's a fish floating in the sky there, and there's hybrid animals everywhere. And it's when you kind of zoom in on this detail, and again, look at this. This is amazing. There's some people inside a glass bubble. There's a rat in a tube there, and there's someone inside a mussel, and all kinds of colourful birds and animals. And there's even something called a doggaroo, which is half dog, half kangaroo. So how does someone come up with that 500 years ago? It's incredibly colourful, incredibly surrealistic and fantastical. And it's got to be like the most imaginative sort of medieval art you can possibly find at a time when everyone else was painting dark, brown, blacks, grey. And here along comes a painting that just broke the mould, completely different. So that was the inspiration for everything. And then after that, I went on a small trip to Salamanca on the high-speed train. And it got me thinking. I was then writing in my little notebook, which I have with me, who else in history has done something like really exceptionally imaginative? And there are lots, you know, my list of 10 grew almost immediately. And then it eventually became 121 great concepts, you know, really imaginative, amazing leaps of thought that just came out of the blue. So obviously, oh, hang on. There we go. So obviously, Hieronymus Bosch is on there. Because, yeah, that's a dancing owl with 4 legs. That takes a lot of imagination to come up with that. But of course, lots of others. So Leonardo da Vinci, exceptionally one of the most exceptional human beings ever to walk the planet. So he was famous for the Mona Lisa, for this picture here, the Vitruvian Man, and you know, about 20 or 30 other really famous paintings. But he was also a scientist. He was also an inventor. If he was alive right now, today, he would be 15 professors, world-class level. He'd be 15 professors in one human being. That's how talented and clever he was. Amazing. Then on my list was growing and growing now. At this point, I'm getting all excited. And I've always been a big fan of someone called William Blake. Does anyone know who William Blake is? Ever heard of him? Oh, yeah, some, yeah. There's a few hands there. But he's an extremely imaginative poet from England, from London, from about 250, 300 years ago, a long time ago. And what he did, he wrote some of the deepest poems you could imagine, but he was an artist as well. And he was really into copper plate printing. So he would actually print pictures and then put the poem and the art together all as one package. And that's an example of one of his pictures there. Does that remind anyone of anything from Netflix? What does that look like? Yeah, exactly. Yeah, Stranger Things. That's the original Demogorgon. So it's from that's almost 300 years old. William Blake got there first. And then the list was growing, you know, computing. We're all kind of taking computers for granted these days, and we all have fantastic computer power inside our phones. But someone like Alan Turing was a British mathematician, kind of started it all. He had the imagination to develop algorithms and the modern sort of mechanics of computing power. Extremely bright person. And then Marie Curie as well. She invented really and discovered a whole new area of physics, including loads of new elements like radium and polonium. So she had a huge amount of imagination, and she's the only human being that's won 2 different Nobel Prizes. She won the Nobel Prize for physics and for chemistry, and no one has ever done that before. Amazing. And then Paul Dirac was on my list as well. Anyone heard of the Dirac equation? Yeah. Yeah, there's a few people that are aware of that. That's something in physics. It's kind of defines the way an electron moves in an atom. So very fundamentally important to the whole world of, again, computers, semiconductors, the internet. Interestingly, he spotted something. He had this equation which he came up with, the Dirac equation, but there was a positive energy solution to that equation, but also a negative energy solution, which he thought about for 2 years, and then he concluded there must be antimatter. he actually predicted antimatter from his own equation while sat in his office in Cambridge one day, realizing, wow, that there must be something. Normally in the universe we have normal matter, but then he imagined that there was something called antimatter, and that's got to be one of the cleverest, most imaginative things that humans have ever conceived. And he wasn't wrong. 3 or 4 years after his prediction of antimatter, this was discovered. It was done by an American experimentalist, and he actually found the positron. So Dirac had predicted there's an electron, but there's also a positron, and lo and behold, he was right, and antimatter was proven and validated experimentally. That's amazing. Switching back to art, this is actually in Madrid. This is the Guernica painting. And someone like Picasso, obviously everyone in the room has heard of Picasso in Spain, and he essentially kind of co-invented Cubism with Braque. And has anyone seen Guernica? It's in Reina Sofia Museum, isn't it? Yeah, it's huge, isn't it? I think it's about 10 meters in width. Very large painting, and it's a protest. It's a political protest against fascism that was, very domineering and dominating at the time, and it was a protest against aerial bombing. So he actually kind of used art almost for the first time as a political message to the people to rise up against that. So he kind of reinvented art using his imagination. My clicker is not working so well, hang on. Oh, there we go, yeah. It's a bit slow, I think, yeah. Who's heard of Jane Goodall? Anyone heard? Oh, loads there, yeah, very good. Unfortunately, Jane Goodall passed away last year, I think at the age of like 94, 95. But she was a living legend of conservation and, studying animals in the wild. And you have to bear in mind, Jane Goodall was about 20, living in London, and she decided one day, I'm going to go to Africa to study chimpanzees at the age of 25, I think. In those days, females in science was difficult, so she had a lot of there was misogyny in the system at that point. And also she was only 25 and she didn't have a PhD. But she had this determination, I'm going to go to Africa, I'm going to live with chimpanzees, and that's exactly what she did. She got funding from National Geographic, and she teamed up with the Leakeys, so Mary and Louis Leakey, who were paleontologists in Africa, and they worked as a team. And then she went off and lived in a place called Gombe, which is where the chimpanzees were based, and she observed a whole troop of chimpanzees in the wild for the first time ever. So she's the first person ever in the world to see chimpanzees using tools, for example, using rocks to smash nuts or using sticks to pull out termites from a termite mound. So the observation of tool usage came from Jane Goodall. So that's fantastic. So she had this incredible imagination, but also a determination to do it as well. And that's very special. And then she spent, after observing chimpanzees and being integrated into chimpanzee society for the first time, and then she spent the last 20 or 30 years of her life devoted to conservation, which on World Environment Day is extremely important. There she is, playing with one of the little chimps in the troop. So it's amazing that she got integrated into a chimpanzee society, the only human ever who can say that. Here's a personal favourite of mine. Anyone heard of Richard Feynman? There's a few nods in the room, yeah. It's a physicist, American physicist, and probably, again, one of the cleverest people ever to work in physics, but also an amazing educator. So he was really committed to educating young people as well with lectures. And there's, YouTube is full of Richard Feynman lectures, which are wonderful to watch. Really interesting guy. But he imagined so much, it's incredible. So he imagined particle physics, Feynman diagrams, he invented those, won the Nobel Prize for that. He also then worked on quarks. Nanotechnology he conceived in the 1980s. And then he conceived quantum computing, which you've probably heard of as well. That's a new form of supercomputing using quantum effects. And he even worked on neural networks and artificial intelligence. What a career that's been. So incredible person. So he's definitely on the poster. And then I kind of like stopped at the internet, kind of like now we're in the sort of modern era. And I think Tim Berners-Lee is kind of displays amazing imagination as well, because he was working at CERN in Geneva, and he really kind of sat in his office one day realizing, you know, all these computers, all these standalone computers that people were buying and using in their offices, he then realized, what happens if we connect them up? What happens if we actually go away from standalone computers to a connected system of computing using the internet? And the World Wide Web is something that he created almost single-handedly. There was obviously some work done in America as well with DARPA. But if you're looking for an individual that had probably one of the biggest impacts in the world, it's probably Sir Tim Berners-Lee. Imagine inventing the World Wide Web and the internet. And when I make my website for the Atlas, I'm still coding in HTML, which he invented. So even 30 years later, it's still the same system. So that's my first list of 10. I'm not going to go on and on and on for 121 pioneers, but it gives you a flavour of, there's artists in there, there are physicists in there are biologists, conservationists. It's a mixture of everything. So it was across all areas of study, all areas of life, all areas of culture. And that's phenomenal. So within a week or so, then, I had this epiphany moment triggered by the Hieronymus Bosch painting. And then I put the poster together and I started grabbing some nice images, designed it. And then I went off to Work Centre, printed the first ever one, put it in my office, my kind of like at home. And then my wife, your chemistry teacher, sat there. She then encouraged me to spread the word. She says, you need to get this out. It's fantastic. So it looks kind of aesthetically pleasing. But then I realized, well, the poster on its own is not, self-explanatory. It needs a bit of context. So then I thought, oh, let's do a website as well. And then within a week or so, this is kind of what's happened now. 135,000 visitors, which is quite a lot for an educational website. From 94 countries around the world. And I'm just amazed when I look at the Google Analytics data of like who's looking at the website in different countries. It's virtually, it's almost the whole world. There's only a few kind of African nations that have yet to look at it. But yeah, it's incredible. Even people in Greenland, people in Fiji, Bhutan, the Mountain Kingdom in Asia, Ecuador, the Galapagos Islands, where there's a Darwin Centre as well. So it does give you the kind of like a bit of hope in the world that there are people out there that appreciate good concepts and good ideas, and also that people love knowledge. Now, I don't think everyone's into knowledge. There are plenty of people in the world that couldn't care less. But I think there's still a significant proportion of the population, maybe 10, 20, 30, 40%, that do care about knowledge, and they do care about human culture, and they do care about inventions and creativity and imagination. So that's really encouraging. And then it kind of got me thinking, well, what is imagination? What is this particular process that all these people have been doing, going back thousands of years? And I think everyone has a kind of a slightly personal or different definition of what imagination is. But I was thinking about it a lot, obviously, and I kind of realized that it's basically, if you close your eyes to the world, and you have a vision, something futuristic. So you're closing your eyes, and in your mind's eye, you can see something that doesn't exist yet, something that's different, something novel, something unique, and something that is within grasp. But just imagining that vision is not enough. You actually need to somehow bring it into the present. You have to implement that imagination. So that would mean, like, you put your words, if you're writing a poem, put it on paper. If you're doing a painting, draw the painting. If you're coming up with an invention, make the invention, make the demo, do the patent. So there's, it's about implementing as well, not just imagining. But that's the core of it. It's really like, how do you bring the future vision into the present? How do you share it with other people so that they can see it as well? Because you don't want to just keep it to yourself. If it's good and imaginative, share it, put it in a gallery, put it on Spotify, come up with a new scientific theory. And then I realized that the same process of imagination that people use in art, whether you're Picasso or Hieronymus Bosch or Salvador Dali, doesn't matter. It's basically the same thing as imagination in science. It's the same process, and it's almost the same purpose. You're trying to understand, like Rob said earlier in the introduction, you're trying to understand something in the universe. And that could be through a poem, through a painting, through a scientific theory, or some invention and creative thought. And it's the same. It's the same as philosophy, humanities. It's the same as music and literature, and the list goes on. Architecture, computing, everything. And this is a deep quote for today. This is from William Blake, the English poet, who said, "The imagination is not a state, it is the human existence itself." That's deep. It's human existence itself. So we are here as humans in order to be imaginative. That's amazing. What a great thing to say. There we go. And then, based on the 10 people that I listed up earlier on, and again, I'm not going to talk about 121 people, but for the subset here of 10, I wanted to know, is there a common factor? What kind of brings these people together? What kind of personalities did they have? Why were they so imaginative? Why were they so good at bringing their imagination into practice? And here you can see everyone from Hieronymus Bosch all the way through to Picasso, Goodall, Feynman, Tim Berners-Lee. They actually do have fairly similar characteristics. They were often deep thinkers. I think that is self-evident, but they were pretty quiet as well. And they had restlessness. They were not quite satisfied with the way the world is, and they had this burning desire to transform the world through their imagination. And they didn't see any silos, so they were very cross-disciplinary thinkers. So they didn't, they kind of refused to see boundaries. And someone like Leonardo da Vinci there, he was the epitome of that. He had no interest in boundaries. It was either interesting or boring, and he focused on interesting. And it didn't matter whether it was fossils or geology or painting the Mona Lisa or making mechanical inventions and devices. He didn't care what it was as long as it was interesting. So these people were very open to ideas, and they really dared to use their imagination. And that's part of it as well. You've got to dare to use your imagination. And I'm sometimes a little bit concerned these days as well. Are young people using their imagination enough? Especially when we've got, the internet is a great, device for wasting time as well. And people spend a lot of time on their phones, of course. Are we actually capturing, the true potential of our imagination today? These people obviously did, and they didn't have too many distractions in their lives. But we've got to be careful that we're not spending all our time on the internet and not using our imagination as we should do. And they were lifelong learners as well. These people worked almost to their deathbeds. I think there's a Picasso museum in Malaga, and there were some paintings on display that Picasso was painting literally a few days before he actually died. He was non-stop. He couldn't stop himself from drawing and painting. And the same is true with, Jane Goodall. She died at 95, I think it was. But she was working endlessly her entire life and learning and learning and learning. That's part of it. Being a lifelong learner is really important. So I think, to try to encapsulate all of this in a really short sentence, this is what I've come up with. They could see the unseen with the power of their imagination. They could see the unseen, things that were kind of invisible to everyone else in the world at that time. And of course, they brought the unseen into the visible world. And thank God they did, because these people, just these 10 people alone, have transformed our lives in fabulous ways. So thank God they could see the unseen. It's remarkable. Okay. So I think if cross-disciplinary thinking is so important, and I think it is, why don't we promote it a bit more? And in school, of course, we have traditional subjects. We have chemistry, and we have biology, and we have geography and art and English and maths. And that's for traditional reasons, so school timetable is split up and you have an hour of this, an hour of that, and the day flows by. And of course, when you go to university, you have different faculties as well. You have a faculty of engineering, a faculty of computer science, faculty of art. And you end up with, creating these silos of knowledge, which is, it's unintentional. It's kind of an inevitable part of the process. But people do get more and more specialised in their fields with time. And probably the most specialised person I've ever met was in America in a conference. And I met this chap who I won't name. And I asked him, what do you do for a living? And he said, I'm a quantum chromodynamicist. And I thought, what's that? I had no idea what that was. I'd heard of quantum, but a chromodynamicist, that's a strange job title. So I've heard of teachers and doctors and patent attorneys and lawyers, etc., but I've never heard of a quantum chromodynamicist. And then he explained what he did, and it was essentially a very specialised field of physics where he was looking at atoms and the nucleus of an atom and looking at the proton and the quarks and the colour of the quark. So you couldn't get more specialised than that. But there's a danger to that. Anyway, he was a nice chap, and he bought me a beer at the bar, so everything was fine. But it's very important, I think, with big breakthroughs and the kind of breakthroughs which are in the featured on the poster. Big breakthroughs come from, not being too specialised. You need to look left and right as well. You need to look up and down, see things inside out, back to front, upside down, and see it from all these different perspectives. So you do need to be quite open-minded, I think, if you're into, coming up with new concepts. And often that kind of transcends different cultures. It can transcend languages and different countries as well. So joining up the dots in a completely new way requires a different way of thinking, and it requires these different perspectives. So that's an important message, especially for young people these days. Okay, right, I'm going to have a quick sip of water. Throat is going. I'm going to give you 4 exciting examples next. So these are examples of interconnected thinking. So I've got 4 slides, but this is mind-blowing. I put this together a few weeks ago, and there are really I get goosebumps even just talking about this. Here we go. Number 1. So we're going to start with art. Are there any people doing A-level art in the room? Yep, there's one. Oh, there's a few, yeah. Anyone else? No? People interested in art? Yeah, very good. So does anyone know the painting on the left-hand side? What's the name of that painting? Pretty famous one. Yeah, exactly, yeah. The Girl with the Pearl Earring. It's a painting by Vermeer, and I think, it's featured somewhere on here. There it is, on the poster. And the one on the right-hand side is actually in Madrid. Does anyone know what that is? I saw that in El Prado fairly recently as well. It's called La Virgen de Guadalupe. The Virgin of Guadalupe is the English name. And it comes from Mexico originally. And it's amazing. When you stand in front of that one, and this picture does not do it justice, unfortunately. When you stand in front of it and you move your head from side to side, it glows and it shimmers. It's like a rainbow. Amazing. Really kind of eye-catching. It's extremely beautiful piece of art. Does anyone know what connects this and this? There is a connection. You know. Any of the students can work this one out? And there's actually a bit of a clue up here as well. Art and biology. So what connects these two paintings? This thing, this. Anyone? I will reveal, shall I? Here we go. Yeah, oysters. This is mussel shells, or it's called an abalone mussel. So these are natural materials. So the pearl is actually something that naturally grows inside an oyster. And this one is massive. That's around about 2 centimeters diameter is the size of the pearl that Vermeer was painting. But it's actually part of this shell system. And it's the same material as here. And it's the same material as here as well. So these shells are natural materials. Now, I'm going to show you this. This is really nice. You have to handle this with care. So I'll pass this around the room. And that is the material that is used. So the inside of that shell was used here. So it's called enconchado. It's the style of painting using shells. So these Mexican artists, and we don't know the name of the person, it's anonymous, but these Mexican artists created these beautiful paintings based on Pacific mollusks. And this is an example of it. Interestingly, this mollusk here, this abalone shell, comes from Chatham Island, which is in the Pacific Ocean, which is named after Chatham, my hometown. So it came full circle, yeah. Now, the question is, right, why is it making this rainbow pattern? Why does a pearl like that have this iridescent rainbow shimmering pattern on it? How does that happen? It's kind of a coincidence, really. You know, the shells and the mussels, they don't get any benefit from, you know, rainbow patterns. It's a bit of a natural accident. But if you're curious, you would ask the question, well, why is it? And then you have to zoom in with a microscope. So this is what mother of pearl, or naka, that's what it looks like under a microscope. It's made of these little hexagons, which are like building blocks or like bricks and mortar on top of each other. And it protects the oyster would probably die very quickly if it didn't have a shell. So would a mussel, so would an abalone. So it's creating a protection system around it in a natural manner. How does it do that? So you've got to keep asking the question of how and why is it, how does it do that? And you just keep zooming in, and then you realize that this nano composite material is phenomenal, because the thickness of these little tiles is somewhere between 500 and 700 nanometers thick, each tile. And that's exactly the wavelength of visible light. So the spectrum of visible light goes from 500 to 700 nanometers. So when you make a material like this, you get interference patterns. That's why you get this rainbow pattern on the shells and on pearls. And that's only kind of evident when you actually see with a microscope what mother of pearl actually looks like at the nano level. So we're dealing with a micro nano material which is biologically made using this. So then you think, how does a mussel or an oyster know how to do that? And it's called an enzyme. So that's the kind of enzyme, and it's called carbonic anhydrase. And we have it in our DNA as well. So we're able to make carbonic anhydrase, but so are oysters and mussels. And it's taken about 1 billion years of evolution to be able to make this enzyme for shells to make this material. And what it does, it's extremely clever. And again, all of this is completely random through natural selection. What happens, the CO2 that's in the atmosphere, some of that dissolves in seawater. And this enzyme, what it does, it turns the CO2 into carbonate, and then it forms calcium carbonate, because there's calcium in seawater as well. So now you've brought CO2 from the atmosphere and calcium in the seawater have joined together to make a material which is super hard and super tough. So the mussel now has a shell around it. It's able to grow a protection system. It's armor plated. And all of that is through 1 billion years of evolution. So around about 600 million years ago, during the Cambrian periods, these shells just exploded. So that's why we get a lot of chalk cliffs. Where I come from in Chatham is full of chalk. Everywhere is a chalk mine. And it's basically just a load of these shells compacted over time. But it's super clever how that is happening. And essentially, it's in the DNA. Isn't that remarkable as well? So these oysters and these mussels and abalones, they have inside their DNA the instruction manual for how to make carbonic anhydrase enzymes and other enzymes as well. So it knows how to make that in its own coding, which is also mind-blowing. And then the weirdest thing as well, in human beings, we also, in our DNA, and everyone in the room right now, we all have around about 50% DNA similarity with an oyster. 50% DNA similarity, which is a remarkable fact. And there are definitely some weekends where I feel 100% mollusk. But today I'm feeling good. But inside our DNA, we've got this carbonic anhydrase enzyme as well. And do you know have a guess what we use it for? Obviously, we're not making shells. Does anyone know what we use carbonic anhydrase for? And you're all doing it now, which is good. Yeah, exactly, yeah. And it's bravo, your biology teacher is clapping you there, good answer. So it's essentially, for breathing, we use it in our red blood cells to trap the CO2 and then release it. So every time you exhale now, when you breathe out, the CO2 is being released because of that, go back one, because of that particular enzyme. So humans and mammals in general, we use carbonic anhydrase for breathing, for CO2 gas exchange, whereas the mollusk world has used it for a totally different purpose, nothing to do with breathing. Isn't that amazing? And you're 50% mollusk. So here's an example. So just to kind of summarize, that's one PowerPoint slide. Got a few more to go, but that's one example where we've got the art world of beautiful paintings with Vermeer's pearl earrings. We've got the enconchado technique that Mexicans developed. All of that's linked to natural materials. We've got optical properties. We've got this rainbow pattern you can see on the inside of that shell. And all of that is understandable. We've worked it out. It's evolution. It's 1 billion years of evolution has been remarkable. And it's all encoded within our DNA, which we share with mollusks. And there's a link also with climate change as well, because CO2 is in the atmosphere. So the question you would naturally think about was, well, if we have more CO2 in the atmosphere due to fossil fuel usage, does that mean we're going to get more oysters, more mussels? Will that sea life increase? Will that compensate? We don't know at the moment. Maybe it will, maybe it won't, but it's worth studying. Okay. Right, a few more examples to go. Number 2. Who's studying mathematics? Any A-level maths students here? Oh, loads, yeah, that's good. Have you heard of Fibonacci sequence before? So if you haven't heard of Fibonacci sequence, I'll just quickly explain what that is. If you take these numbers here, if you do 1 plus 1 equals 2, 2 plus 3 equals 5, 3 plus 5 equals 8. So you can just keep doing that essentially forever. So 55 plus 89 is 144. Anyone know the next number here? Quickly work that out in your head without a phone. 33. Close, yeah. But yeah, you had the right idea though. 89 plus 144. So you're always basically, your new number is the sum of the last two in the series. And then other people picked up on that. Even Leonardo da Vinci was very impressed with this Fibonacci sequence from 800 years ago. So another Italian got involved. And people started drawing spirals. So again, if you take these numbers, you do 1, 1, 2, 3, 5, 8, 13, 21, and you just keep going like that. You get something called a logarithmic or Fibonacci spiral. And again, it appears in nature. It appears in these shells, these nautilus shells. It appears in pine cones, the way that sunflower seeds pack inside a flower. It's just everywhere. Loads of Fibonacci sequences in nature. And interestingly, it appears in art as well. So if you take 144 and divide by 89, so now you're doing a ratio, or 89 divided by 55, you end up converging on a number which goes on and on, but it's basically 1.618 is the golden ratio, and it appears in art. So lots of artists have used that in history, including people like Hokusai and Da Vinci, and also in architecture. So if we, there we go. Does anyone know where that is located? And it's in Spain, so there's a clue. Anyone know where this staircase is? The Fibonacci staircase. This Spanish architect was obsessed with Fibonacci. Very good, yep. So it's in Sagrada Familia. So it's Antoni Gaudí. There it is. So he installed these spiral staircases as part of his design because he was so interested in that kind of underlying mathematical structure. So again, we've got mathematics having an influence on nature. Again, it's probably in DNA some way, but also on art, paintings, and even buildings. Now, can you think of anything that's much, much bigger than a cathedral, bigger than the planet? Well, if you keep going bigger and bigger, you eventually end up with, that's the Andromeda galaxy, also has a Fibonacci spiral on its, these spiral arms. There's a massive, a supermassive black hole right in the middle. And these are all stars. In that photograph, there's 1 trillion stars. 1 trillion stars, and you can actually zoom in on them. There's a European Space Agency website with a Hubble photograph of the Andromeda galaxy. You can zoom in on it. And yeah, so it's 1 trillion stars, and therefore many trillions of planets. So we are in our solar system with our sun. Imagine 1 trillion of those. Well, that's just one galaxy in the universe. Massive. And if you travel from here, on the left side, over to the right side, that will take you 200,000 years to travel at the speed of light. So 200,000 light years to go from there to there. That's insane. And for some reason in nature, nobody really understands why. No one's got any particular clue about why that is. But again, these logarithmic spirals, they almost perfectly define the arm of this rotating galaxy as it disappears into a black hole. That's mind-blowing. Just the scale of it is mind-blowing, but the fact that there's some underlying mathematical structure that we can actually analyze and look at. But again, it's just one of the mysteries of the universe. We just don't know all the answers. And there's a really, I don't know whether you've heard about this discovery. This is really recent stuff. This is discovered. Click on there. Oh. Yeah, these are superstructures. These are galaxies. So that Andromeda galaxy would just be one galaxy like that. We've just discovered that there are rings of galaxies in our universe, and that's only just been discovered by someone only a bit older than the students in the room here today. Have a look at this. So that is Alexia Lopez, who's now a doctor. She discovered that at the age of 24. Amazing, isn't it? She's obviously a very happy 24-year-old, having discovered it. And this chap is a guy called Roger Penrose, Sir Roger Penrose. He's a British mathematician and physicist. He's a Nobel Prize winner of physics as well. So he's a very, very clever, imaginative, big name in the world of science. He's 94. And she's in her 20s. They've teamed up. They're teaming up on this particular discovery because Alexia Lopez has discovered it experimentally using something called magnesium absorption spectroscopy. And it's a way of looking at the night sky through a kind of a new lens, new goggles. because this is the plough here, by the way. That's the plough, what you would see visibly. But when you put the goggles on, you see this extra superstructure that's only just been discovered by Alexia. And the reason Roger Penrose is interested, because he has a mathematical theory of the universe, that we have an eternal universe where you have a Big Bang, and then everything expands from that Big Bang to the point where it can't expand anymore, and then you trigger a new Big Bang. So it's an endless cycle of universes. And the theory is, and they don't know exactly why, but these could be remnants from a previous universe. How about that? So before our universe began, these could be leftover signatures from a previous universe. And that's something that they're now working on. Hopefully they can validate that in the coming years. You know, the jury is still out, but they're researching it actively. But it does seem that this discovery, these two rings, that does seem to be a real fact, not some kind of statistical accident or fluke. And the theory of CCC, which is conformal cyclic cosmology, you know, that obviously needs evidence. So they're teaming up and they're working on it. But there's a 70-year age gap between a Nobel Prize winning 94-year-old physicist and someone in their 20s. Isn't that remarkable? Really, really special. Anyway, I thought I would mention that. I kind of added that at the last minute to my presentation because I thought the message here is really powerful. These people are studying the universe, you know, gathering evidence, trying to come up with theories of how we've existed and what is the whole kind of mathematical structure to the universe. And, you know, it can happen at any age. You can be a 20-year-old or a 90-year-old. Doesn't matter, but they're using their imaginations. That's really good. Okay. Number 3. This one is really special. And your biology teacher, Dr. Garcia here in the front, is already getting excited. I think you did your PhD on this topic, didn't you? So these are really special. And the museum here is fantastic because downstairs, I don't know whether you've had a chance to see it, but hopefully we can show the students the section of the museum that houses these pictures. Does anyone know who drew these pictures? Very famous Spanish scientist. Yeah, exactly. Ramon y Cajal, very good. So Santiago Ramon y Cajal, around over 100 years ago, worked on the brain tissue. He had this imaginative process of like, what's inside the brain? He looked at rats' brains, rabbit brains, human brains, and he started to draw things. But there's here, actually, is a microscope. That's one of the first microscopes he would have used in that cabinet there. So it's a very simple single lens microscope. When you slice a brain, when you have a brain slice and you put it on a microscope slide and you look at it, you don't see too much. You have to actually stain the specimen. You actually have to make it black. So he invented this. So he had a silver chromate chemical, which he stained and made everything black. So before you couldn't see anything, you couldn't draw it. And all these pictures here, you know, essentially his work. He was defining and drawing with great meticulous artistic skill. He was, you know, creating these two-dimensional structures. Before I go forwards, hang on. And we're very lucky because this is an original. So that is one of his original drawings. Oh. Dr. Garcia is getting emotional now. But that is a beautiful piece of work. And so I'm going to pass around a replica of that. So that's a copy of the original. Pass that around. Maybe we'll pass that on this side. How nice is that for a drawing? I mean, people sell these on Amazon and Etsy, so you can actually have these as posters in your house. You know, they are, you know, artistic and aesthetically pleasing. So these drawings, these represent some of the first images of what the brain looks like at the cellular level. So each one of these is a neuron. So There were theories of how the brain works, and Ramon y Cajal actually proved that these are individual neurons, and they have synapses, so they connect up with something called a synapse. Now, the human brain, all of us in the room have got around about 86 billion neurons in our brains, which is a huge, huge number. But each of these neurons is branched. When you count up the number of synapses in your brain, you have 100 trillion synaptic connections inside your brain. It's incredible, isn't it? So our brain is just this parallel supercomputer that's been created by nature. And of course, we come from hominids. So here's an example. We have a paleontologist in the room here. Magnus is your name, isn't it? Marcus, yeah. So Marcus has kindly, well, he's 3D printed these previously. And this would be a hominid skull. Is it Homo habilis? Ah, okay. From Ethiopia or from Olduvai? Yeah. 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 Yeah, right, okay, yeah. Yeah. Ah.
And we thought makes a nice complementation to your poster.
Yeah, thank you very much, yeah.
Particularly famous for the very, very big teeth, the very, very small brain.
Yeah, and the small brain, you can see that. I'm going to pass this around as well. Be careful with it, of course, don't drop it. But the small brain, yeah, we've got 86 billion neurons in our brains as Homo sapiens, but these earlier hominids only had about 25 billion neurons in their brain, so it was significantly smaller. But it's still essentially the same structure as what we see here. And then as the microscopes got better, so that microscope there was a great starting point, but you can do even better with an electron microscope. Where's my thing gone? Oh, there it is. So electron microscopes were developed, and then you can get three-dimensional information, and then you realize the whole thing is just this massive network with these 100 trillion synaptic connections, all doing thinking. But we don't use all our neurons at the same time. Your brain would literally explode if you did that. So when we're thinking or talking, like I am now, you'd be on about 1%. Your human body just cannot handle the amount of energy. You wouldn't have enough food in your body to sustain 100% of your neurons. So when you're active and conscious, you're only using about 1%, which is quite amazing, yeah. And then there's a really interesting connection then. As the understanding of these neural structures became evident through microscopy, through great anatomy and fantastic biological experiments, the mathematicians got involved. So the mathematics people realized, oh, maybe we can actually develop computer models that can replicate how the brain works, and that's called a neural network. And lots of scientists have worked on that, including Richard Feynman, who I mentioned earlier. I'm going to try my best to explain how a neural network works. So you have an input layer, and that is, the outside world is giving you information through your eyes, through hearing. You might have a smell, you might touch something. That's called the input layer. And then at the other side, you have the output layer, and that's a decision. That's you've got an outcome, a prediction of an outcome. And that could be it could be a number, it could be a smell that you recognize, it could be, a voice that you recognize, it could be your wife or your husband's voice, and that's the output layer. And then in between here, you've got your 100 trillion synaptic connections all firing, well, not all at the same time, but you have these kind of hidden layers, they're called, of synapses, which provide signals and information through the network. And that's where the pattern recognition is happening. So that if you smell through your nose, that's the smell of cut grass. Oh, that's my cat meowing. Oh, that's the number 5. So you kind of recognize things through learning. And there's a feedback loop in here. And there's something called back propagation that was invented by Geoffrey Hinton. So there's all kinds of little tricks, mathematical tricks that we can use to replicate how the brain works. So I'm going to give you an example, right? Everyone in the room, if you could stare at this square here, I think it goes without saying, we know what that number is, it's the number 2, right? But this is how it works. This is what you're going to be kind of unconsciously doing. So stare at that. There's 28 pixels there and 28 pixels there. So there's 784 pixels of information will go into your eye, goes through the lens, it hits the retina at the back of the eye. Black and white information goes into your rods. That information goes into the optical nerve, and it goes to the base of your brain here, called the thalamus. And the thalamus then distributes it to the other parts of the brain, like the cortex. And what's happening is the information flows into the inner layer, that first layer there, and it gets processed. And because we've all been to school and, through kindergarten and through primary school, we've all learnt to recognise the shape of the 2. So there's a squiggly hook there, there's a diagonal there, and it's flat at the bottom. So we know from our early learning and going through school that is the number 2. So by the time it gets over here to the output layer, your brain just automatically says, oh, that's a 2. It's not an 8 or a 0, or it's not the smell of cut grass or basil or a cat meowing. It's a visual signal that will always be decided upon. It's the number 2. So you know what that means then. And that's how it works, and that's how a neural network learns. And there's, like I mentioned, there's feedback loops and back propagation, there's error correction in there as well. But what I've just described is really the basis of a neural network. And that can now be transferred into computer code so that we can actually start using that for learning. There's something called deep learning. Everyone recognize that logo there? Yeah. Anyone using it for their homework? Oh, no one admitting to it, at least. But that's ChatGPT, and that's one example. Many other like Google Gemini and Claude. So these are large language models based on deep learning, and they're able to take information from the internet, and they're able to learn. And so that has now triggered the whole industry. And everyone's talking about AI these days. The whole AI industry originates because of that, which is amazing. If Ramon y Cajal hadn't drawn that picture, hadn't bothered to look at the structure inside our brains, we wouldn't have AI. Maybe someone else later would have delayed the whole process. But the fact that happened, over 100 years ago, has now triggered the mathematics, the computer science behind all of that. So again, we've got these artistic drawings, which I think are passing around, of anatomy. There's chemistry involved in it, there's structure, the microscopes were needed as well. And then along come the mathematicians, they're doing data science, they're doing computing, and now we've got AI, which is amazing. So that shows you that the history of ideas, if you understand them and you can connect the dots, can lead to the future of ideas as well. And that's one of the themes of my presentation. Now, of course, things are going full circle. Now, AI is being used in hospitals. Doctors use AI all the time. If you go to a neuro-oncology department, people that are studying cancer and brain tumours, they're using AI now. Whoops. They're using AI right now in hospitals because AI is better at identifying early tumours than humans are. So we can actually use that to treat brain tumours at an earlier stage than otherwise. I mentioned at the beginning, my friend died of Huntington's, sadly, and AI is being used now in Huntington's research as well. The drug design for neurological diseases like that, which are, genetic and very rare, but AI is now able to help in that area. So there's lots of kind of gene therapy treatment, which is kind of assisted with the help of artificial intelligence. So it shows you that it can go full circle. You study the brain, You create AI, and then it helps you understand the brain and treat it medically as well. So it's a full circle. It's incredible. AI has lots of other uses as well, and we'll come to that later. Right, I need a breather and a bit of water. So you'll probably be pleased to hear this is the final example. Here we go. Number 4. So today is World Environment Day, and that's not a coincidence. We chose today for this presentation. So there's a meeting taking place in Azerbaijan, in Baku, and the theme of today's COP meeting is climate action. And my God, we need it. We need action. And I think, one of the things that I'm emphasizing here is that we need imagination, but we need to actually implement the imagination as well. We need to have people that can create new ideas, but we need action, we need agency, and we need some way of implementing it and getting things done. And that's really important. And the reason I say that, because if you don't have imagination, well, you're not going to come up with good solutions or ideas. And if you can't be bothered to implement them, when you're going to end up with nothing. You will have climate change will continue and continue, and the alternative is horrible. I mean, the alternative looks a bit like that. That's not the future I want to see. That's not the future you guys want to see. Nobody wants this happening. This is actually a real picture from a golf course in Washington State in America. And these guys are sort of happily, finishing off their round of golf, while the background is like burning down. You've got a forest fire right there, and these people are staring at the forest fire, but these guys are kind of like happily finishing off their round on the 18th hole. That is not the future. We don't want to see that. So what are we going to do about it? So we do need imagination and implementation. And I'm optimistic, and I remain optimistic, that we can do stuff. Now, there's a fantastic organisation in the UK, which is called UK Atomic Energy Authority, and they've been given the remit by the UK government. You guys will develop the nuclear fusion reactor of the future in the next 10 or 20 years, and it looks like this. Now, nuclear fusion is exactly the same thing that happens inside our sun. So the sun is obviously very powerful, very energetic, gives off a lot of energy. And inside the sun, you have a fusion reaction between hydrogen isotopes. And those hydrogen isotopes, we can create them. We can actually, those isotopes are available to us. And if we fuse them together and we can control this solar reaction inside a big metal chamber that looks like that, this will give us energy, essentially clean, limitless, no CO2 energy forever. It's that important. And the physics behind it is established. We've proven it. There was a first reactor called JET in Oxford that proves that it works. You can actually create energy, more energy than you put in, is proven. So we know that it can work. Now, this is super important right now because, especially on World Environment Day, if there's one thing that you remember from my talk today, burn that into your memories. So what we're doing today is 4 million times worse than this. A fusion reaction delivers 4 million times more energy per kilo of fuel than burning coal, diesel, gas, oil, petrol, all the fossil fuels that we have today that we've kind of inherited from the Industrial Revolution. That's amazing, isn't it? So it's not like, oh, this is like 2 or 3 or 4 times better. Try 4 million times better. That is worth working on, right? And then to put another kind of perspective to it, if you could bring together all the coal, the gas, the oil, petrol, diesel, everything, if you could bring all of that together, all the known reserves on planet Earth, you would fill up 4 million supertankers. These big ships that travel the world. That's 4 million supertankers worth of fossil fuel that we have left on planet Earth. And at today's rate of consumption, we're going to burn all of that in around about 70 years from now. So in 70 years from now, those 4 million supertankers will be burnt, and it will all turn to CO2, horrific climate change. And in your lifetimes, you know, I'm probably not going to live another 70 years, but you guys will. You know, we're going to run out of fossil fuel anyway, because it's a finite resource. It's a finite resource that happens to have a lot of pollution and climate change problems as well. So it makes evident sense to get off it, stop the addiction, move on to something else. Now, the 4 million supertankers that I've just mentioned, if you turn that into nuclear fusion fuel, these hydrogen isotopes, it's less than one supertanker will do the job. One supertanker of fusion fuel is enough to save mankind. So humanity, really, like the future of humanity, rests on these kind of technologies. Of course, we can do other things. We can do solar, we can do wind, we can do geothermal, but none of them have this level of energy density. 4 million times better than chemical combustion today. That's hard to beat that. But of course, these fusion reactors, nothing's ever easy, so they're complicated machines. We've only built a few of them around the world, and we know that they can work, but we need to get them working for like long duration. We need them to work for days, weeks, months, and eventually like 20 years, like a proper power plant making electricity. And you can't just build them out of anything you want to. You have to use special materials. And that's where me and my wife came into this. So we got, about 2 or 3 years ago, we were kind of contacted by the UK AEA. They actually specifically called us up and asked, can you guys make this new material? Didn't exist, you can't buy it. It's not commercially available, it's not on Amazon, and it's a material that is made of tungsten and boron. Now this is a mineral, this is a Spanish mineral. I think I'm allowed to pass this around, so I think you can't really break that. But this is reasonably heavy. If you pass that around, it's called wolframite. It's a tungsten mineral. There are lots of these in Spain. There's a massive mine near Salamanca, actually, making tungsten ore. I won't pass this one around, it's a bit bigger. But this is boron, or boron mineral. It's a little bit lighter and a bit more transparent than that one. But these are materials, or critical materials of the future, because we need tungsten to protect and shield the inside of this. I won't go into all the details of why we need to do that, but we need a shielding material. And tungsten, is being very heavy, is very good at kind of absorbing X-rays and gamma rays. And boron has a very special property. It's good at absorbing neutrons. So if you make a material out of tungsten and boron, and that's called tungsten boride, then you can use it in this central column here to protect all of the equipment so that it lasts for 25, 30 years. If you don't have a material like this for shielding, this will last 10 minutes. Everything breaks. So you need to develop this special material. So we were contacted by them specifically, and we went away, and it took us a while, it took us a year or so, and we made this. This is the world's largest block of tungsten boride. My wife is getting all embarrassed there, hanging on to this. This is the disc here. It's the only piece of material of its kind in the world, and it's really complicated to make. It's being tested by these guys right now. They've been testing it for over a year, and it's passing all the tests, which is good. But they're going to test it for 4 more years. So in about 4 years from now, we will know whether this receives the full kind of validation from the organisation up here. And if it does, and if we're hopefully, fingers crossed, a bit lucky as well, if that material turns out to be a really good radiation-resistant material, it's going to get used in the 2030s. It will become the fusion-grade industry standard for all fusion reactors in the world, which is a remarkable achievement. But we have to be patient, we have to do lots of testing, we're still working on it. And this is what it looks like under a microscope, and this is a special electron microscope where you have transmission as well. This material is made up of loads of randomized little needles all stuck together So it's fully solid, but you've got all these kind of needles, and it looks totally random. And it reminds me a lot of this. That's a Jackson Pollock painting. When you kind of toggle back and forth, it does look a bit like that. And the fact that it's random nanostructure is really important for its properties. It survives radiation better. So it's going to do a good job, we hope. So again, we're talking about minerals from the earth that we need to access and have control over. We need these special nanomaterials with nanotechnology being developed. If we can develop a new, clean, limitless energy source on planet Earth, and we can literally bring the sun and put it under our control, then humanity is essentially saved. We will have clean energy forevermore, and it will bring humanity to a whole new level. We are used to chemical combustion in our cars, in our homes, in our power plants and factories. We're burning stuff, and we've been burning stuff for like 300 years. But if you can do 4 million times better, that's worth working on, right? And I think this is an important document as well. This is something that's free of charge. It's on my website. I've analysed over the last 2,000 years all of the clever concepts that have gone into a fusion reactor to make a fusion reactor even conceivable at all, to make it even possible. And it goes back a long way. You know, there's a lot of history, and it goes from 1 all the way down to 9 and then back into 10 here. And it analyses all the clever ideas, the clever people, all the great things that have happened for, you know, a few millennia that will unlock this wonderful machinery, this wonderful fusion reactor. And I'm very, very hopeful that this is going to work. And it really does need to as well. So there's a fantastic example, again, of the history of ideas will become the future of ideas. That's worth remembering as well. You have to understand the history of all the things that have happened step by step, because knowledge builds upon other knowledge, and bringing all of that into a nuclear fusion reactor will be a fantastic achievement. It'll be the best thing that humans have ever made. So we're very, very hopeful. I should also add that, you know, the UK AEA is one organisation. There are many others as well. There's lots of companies and various startups working on it as well. I think there's about 40 reactors currently being designed around the world. And fingers crossed, all you need is one of those 40 to work, and we're saved. And if anyone's particularly interested in this topic, you can chat to me afterwards. I can point you in the right direction. There's lots of good university studies and particular universities that are, you know, working on this topic. So if that kind of floats your boat, let me know and I'll point you in the right direction. But feel free to read this document. It's free of charge. It's available. It's on the website. So have a look at it. And even if you're not a physics geek or guru, it doesn't matter. Have a read of it anyway, because it's fascinating. Okay, final thoughts. I think hopefully I've shown with the 4 examples today, you know, that there's a lot of intersection between art and science and humanities. You can see it all coming together really nicely. And then the important thing is get rid of the silos. Don't see the world through different subjects. You need to start to think in a very cross-disciplinary way and have no distinctions. Knowledge is very cumulative. It usually builds up over thousands of years. It's very impressive the way it does that. And it is layer by layer. It's almost like a 3D printer of knowledge. And the history of ideas does serve us, and it gives us a great blueprint for the future of ideas as well. And I think, you know, the Atlas, even though it's just a poster, it's actually more than a poster. It's much more than a poster. And I'm very happy that I've developed it, and I'm happy that people around the world are looking at it and interested in it. And I do get emails from people all around the world saying, that's a great idea, well done. And it's a good idea about great ideas, essentially. That's what it is. It's a good idea about great ideas. And what it does, it shows it visually, so it looks nice. It's chronological, because this is, like, you know, that's 4,000 years ago up here. And it moves chronologically all the way down to the present era, things like CRISPR, you know, the kind of life science discoveries for gene editing. So it's chronological, and it's all shown in a very cross-disciplinary way as well. And I think the most important thing really is that imagination is the key ingredient for creativity. And imagination, we've got our 100 trillion synaptic connections in our brain. It's very powerful. It's much more powerful than you can ever imagine. It's extremely powerful. And the good thing about imagination is when you start to use it and you get good at using it, it gets better and better. So you can actually train your process of imagination. It gets better the more you use it. And if you don't believe me, here's someone way cleverer than I am. And this is a quote from Albert Einstein. He said, "Logic will get you from A to B, great, but imagination will take you everywhere." That's different. So on that note, on that bombshell, I will end. So muchas gracias. Thank you very much. Oh. Thank you very much. Before I forget, I do have a couple of extra slides here, just to show how much I've written on the website. These are all free online resources for students, especially for A-level and IB students in particular, so your age group. These are all the things that I've written about, so there's about 1,000 pages of free content. Feel free to read it, use it. Is it being used in your school already? I think it is to a certain extent, isn't it? Yeah. So yeah, this will probably start being integrated into your courses. I know at UEX we're using it as well at the university. I wanted to show that as well. So that's a bit of an advert for UAX where I'm based. And in our library we have an Atlas of Human Imagination poster up there, which is helping inspire our students. And I know Lucia, one of our lecturers at the university and one of my co-collaborators, she uses it in some of her courses as well on things like 3D printing, right? Yeah. So it's kind of like it's being absorbed into different curricula, and I get very nice feedback from teachers around the world in all kinds of funny places as well, places that you would least expect, and people are really kind of resonating to this. So it's a kind of it's a new way of looking at education, looking at knowledge. And I'm going to stop talking because on the next slide, I think it's time for some imaginative questions from you guys. So we do have another microphone somewhere. Is that right, Carlos? Oh, yeah, Gemma's got it. So who wants to start? Anyone have any interesting questions? On anything you like, I don't mind.
So I had a question. At the start of your speech, you talked about matter and antimatter. And we know, like, if I use your example of fusion, we know that in a star, there's a hydrogen fusion, and when there's no more hydrogen, there's helium fusion. But those are the forces that are expanding the star, and there's gravity that is pulling it in. But what I'm trying to say is that there's forces balancing this, and we also know the forces acting on matter, on atoms. And I was wondering, what do the forces look like on antimatter when there's a positron? What specific conditions does antimatter require? And if we are ever going to be able to use antimatter to expand our knowledge on the universe?
Cool. Well, that is a great question, and it deserves a great answer. And I don't think I can give you that great answer. I'm not involved in the field enough to know all the sort of fundamental forces of antimatter. I mean, there are four forces in nature. So we have things like gravity, electromagnetism as well, and there's a nuclear forces as well, sort of strong and weak. And I understand that they do also operate in the same way with antimatter. But yeah, that's a very deep question, and I think people are still trying to work out the details of that. That's why we have these things like, the Large Hadron Collider at CERN and various other particle accelerators. They're trying to work out the details of all of that using things like Feynman diagrams, which can show you how things interact. And there's also, did you mention dark energy and dark matter? There's another aspect to all of this as well. So you've matter, antimatter, but then there's something called dark matter as well, which is completely unknown. We know it's there, but the details of that we don't understand yet. So it's very early days. But that's why it's important that we do this kind of research, so that we can get to the bottom of it. Maybe dark energy or antimatter becomes very important for things like fusion and energy production in the future. So very, it's worthy of studying, because these are fundamental questions in our universe about energy and matter. Okay, next question.
Okay, it's sort of a comment and a question. Are you aware of the work of Ian McGilchrist? Because, he's this British psychiatrist who has resurrected the unfashionable idea of the different hemispheres, and how one, in his view, is sort of looking outwards and trying to put everything in context. Cross-disciplinary. And the other context is much more focused on systemizing and mechanics, and it's the balance between those that allows for creativity. And his book, I guess it's 2009, The Master and the Emissary, is things are much better when the hemisphere that is looking at context is in charge. And that's, I think that's what your message is here, that you're saying imagination is unlimited and it's a resource and we have to let it free.
Yeah, so
it's sort of a comment more than a question.
That's in the field of psychology, is it? So
he's a psychiatrist.
Parts of the brain, for example. Yeah. I've not read of that.
Well,
I'm not aware about that. Yeah, but it sounds really.
But it's the same. I think you're saying the same thing.
Same message, isn't it? Yeah.
And thank you. Very good talk. Really excellent.
Yeah.
So.
Yeah, I will read that now. Now that you've mentioned it, I'll get the reference from you. Yeah. Thank you.
Thank you.
Any more questions from the students? Here's one. There's a microphone coming.
Are you planning to update the Atlas of Human Imagination, or do you think that's like the final version?
Yeah, when I created it, I did a 10 by 10 grid initially, and that was 100. And then I thought, oh no, I've missed out a few really good ones. So then I updated it to 121, so it's now 11 by 11. But I'm going to do an update of that, and I'm going to add a few more people on there as well. So I do plan to update it. Obviously, it takes time and energy. I will probably do that in maybe this year or next year. But I do plan to add a few people to the list as well, because there are some great concepts which I think are missing, which would be nice to include as well. So it's kind of a living, growing, evolving project that will change with time.
You'll ever take any away?
Sorry, I can't.
Do you think you're ever going to take any of them away, or you're just going to keep adding?
No, that would be rude. I'm not going to remove anyone. No one's going to get deleted from the poster. And obviously, it's my personal take on the world. And it's a selected curation of ideas. But by and large, there's a lot of good stuff in there. Like Darwin's theory of evolution is in there, and all the life science breakthroughs for vaccines, and so it's pretty comprehensive already. But I think it will be extendable in the future, and it'll be a nice side project for me to keep updating it on a sort of maybe on an annual basis. Yeah. For now, it's fine, and there's no cancel culture. No one's being deleted, so that's good. Okay, any questions from this side of the room? Maybe I have to point to someone and ask for a question.
Perhaps.
Question from you, please. Oh, here we go.
It's not very interesting. I'm just curious as to the properties of boron and tungsten that make them resistant to radiation and to absorbing neutrons, and why do these properties not disappear or change once they're combined into tungsten boron? Yeah,
they're actually atomistic properties. So when if you have A tungsten atom is very good at absorbing an X-ray or a gamma ray, and that's because it has a very big Z number, so the proton count is large in something like tungsten. So that's known. So tungsten on its own is fantastic. And then boron has a completely different atomic property, and especially boron 6. There's an isotope of boron number 6, and that one is very good at absorbing neutrons, and it goes from boron 6 to boron 7. So it mops up neutrons, and in a fusion reactor that I showed, loads of neutrons are being emitted as part of the reaction. Neutrons are bad news for regular materials. They destroy steel and everything else. So you need to mop them up and then kind of lock them in place, and that's what boron is very good at. And then the second part of your question is, well, what happens when you turn it into a material and you actually make a compound? You still get the same atomic level properties, even though it's now bonded together as a chemical compound. So tungsten boride is actually slightly better than tungsten and boron as pure elements, because the crystal structure plays a role as well. So tungsten boride has a very small crystal structure. The lattice spacing of it is very fine, so you get more bang for your buck. You actually put more atoms in there than you would if they were pure elements. So it's a condensed form, which is really special. And the material has been radiated at this lab in Oxford, and it's passed all the tests so far. And even when the boron mops up the neutrons and there's a little bit of expansion of the material, it doesn't break, it doesn't crack, it doesn't disintegrate into powder. And that's important if you're building a nuclear fusion reactor that's supposed to last for 25, 30 years. You don't want cracks, and you don't want metal parts to turn into powder. So it's very important to make these compounds, have them tested, but it all revolves around their atomistic properties and how they interact with neutrons and how they interact with gamma rays.
Thank you.
There we go.
Thank you very much. First of all, it's been amazing. And it's been, I think, very eye-opener for all of us. I have a question more on a philosophical, maybe academic point of view. Have you encountered in your many viewers comments or any approach from education, as in my thoughts were, we are teaching in a very old-fashioned manner. Yeah. We are really teaching in an old-fashioned manner. So has any educational institution maybe approach with the idea of, are we in a point of changing the way we teach, changing the curricula, can we kind of make from the ground changes such that we start teaching in a modern way, like cross-disciplinary? Because I'm just listening to the tungsten and the boron. Come on, we're teaching that the 3 particles in atoms, right? Subatomical particles. And we're really teaching in an old-fashioned manner, don't you think? Students, don't you think? We are really learning and teaching. So is there any approach from educational institutions to make the leap and to just try and change? Have you heard about, are you involved in any project like that?
Yeah, I mean, that's a great question. I mean, the world of education is very traditional, very slow-moving, and not massively open to change. So that's your kind of starting point. So if there's going to be change, it will be slow, unfortunately. Some countries are better than others, I would say. Some educational curricula are better than others as well. I know IB are very interested in this whole theory of knowledge, cross-disciplinary actions, but I mean they can do that in A-level as well with things like general studies and particular kind of group projects. And there's something called STEAM as well, which is science, technology, engineering, art, and the M is maths. So STEAM is becoming quite popular as well in different countries, but I think unfortunately it's a very slow pace of change. I have been in contact with other educators, university people, and also with school teachers as well. Haven't been approached by anyone from IBO yet, but it might happen. But the feedback so far has been massively positive in the sense that why aren't we doing more of this? Why aren't we doing this cross-disciplinary projects, cross-disciplinary thinking, this kind of creative approach that I'm talking about. And, you know, I'm probably not the only person in the world promoting this. There'll be others as well. But why aren't we doing more of that? Because it's firstly really interesting and fun, but also really useful. It gives you a new way to see the world. And if you can see the world in a different manner, that helps you as a researcher, as a scientist, as an artist, etc. So I think it is very important to, you know, philosophically keep promoting this because it will do our education system well. I think it will serve us well in the future. And I think, you know, because of the traditions of education, you know, the education systems that we have now were invented 100 years ago. And, you know, and there was very specialised school teachers that you could employ. You would divide up the school day into several hours, and you might have 7 or 8 lessons in a year, over the course of a day. So that's just tradition that we've inherited, but there's not a lot of people thinking, oh, let's just merge stuff together a little bit. Let's do joint projects. Let's do these examples that I showed today, these 4 examples. They're enormously cross-disciplinary. And that was the whole point of me showing them, you know, and that would be nice to see that thinking replicated in schools for the benefit of students, because students do resonate to that. And you don't need to be an expert in every single thing. You know, I'm talking about nuclear fusion reactors, but there'll be people in the room here that have no idea what I was talking about with physics, you know. But that doesn't matter. It's important that people still understand something about it, even though you might not be a fusion specialist yourself and that's not your career path. But it's really important to understand something about it rather than nothing. And that's the danger. If you have silos in a school, you might end up with nothing. No one's ever heard of a fusion reactor. Okay. Right. Let's do one more question, and then
anyone
I'm done.
else? Yep.
Oh, here we go.
With your company in Norway, researching all about the nuclear fusion and stuff, are you hopefully planning on finding yourself on the Atlas in the future? By
me personally? Oh, no.
Hopefully discovering something.
I would be very vain and very self-important if I said, yes, I've reserved a spot for myself. No. I think the people that have contributed to humanities knowledge are way, way better than I am. I know my place in society and fairly prominent in the world of material science, but I'm not going to big myself up and put myself on the poster. I'm too humble for that. So no, I will leave it to the other 121 people that have done great things for humanity. Yeah. What a funny question. Didn't expect that one. Anyone else? Oh yeah, one more here.
You mentioned at the start that in your lifetime, you worked a lot in different environments, but all in research. I was wondering if you could talk about your different experiences and what you have observed, how research is differing in different types of workspaces.
Well, that's a good question. Oh, that's brilliant. That's a great question as well. And I'm going to give you a great answer as well. How long have we got? I could write a book on this. I think, and, you know, I'm unique in the sense that not many people in the whole of Europe or the world have ever worked in that many different types of R&D environments. So I can speak with some authority on the different types of academic research, governmental, intergovernmental, large industry, small industry as well with startups. So I've kind of seen all of it. Now, the way I see the world of research is that you have like a circle, and you stand inside that circle. That's a circle of the known information, known knowledge. And when you're a researcher and you're a scientist, your job is you've got the circle, the perimeter of the circle, and you need to step out beyond that circle. So now you're entering the unknown. So you spend your whole career, like your normal life inside the circle of known knowledge. But when you go to work and you do your experiments and you do your theory and you do your modelling and you do experiments every day, you're always doing this. You're always pushing beyond that line. And that's a fantastic place to work. And I would encourage that. If that's your mindset, go for that as a career choice, because it's great. It's never boring. Working in the unknown is fabulously interesting, and you might discover something brilliant, like the 24-year-old student Alexia Lopez, who discovered the biggest superstructure in the universe. So, that idea of, like pushing the barriers and the boundaries of knowledge is really important. Now, each organisation that I've worked in has done it slightly differently. They have different priorities. Now, if you work in a startup company, it's creative, but it's chaotic creative. So you don't have all the resources. You need to be very resourceful. You don't have billions of euros of funding. So you have to be extremely careful with what you're doing, and it can end up being a little bit chaotic as well. And that's fine, that's normal. If you work in a large company, it's much more structured, much more corporate, many more meetings are involved. Committees start occurring. You need to get approvals every time you want to do something. And that can be actually quite cumbersome. So working in a very large organisation can hold you back somewhat. Things go a bit slower. They're not as fast-moving and creative and somewhat chaotic like a startup is. So that's how industry operates. And I've seen both of those in my career. And then with academia, you have total freedom. You can design and conceive and come up with whatever you want to, as long as it's interesting, as long as it's publishable, as long as it's accurate, as long as other people are going to be interested in it. And you'll get some citations, and you'll end up, there's things called H-indexes that scientists have. So there are metrics to the quality of your research. So academia has a certain style of working, and these days it's become very kind of like measurable, and that's can be good and bad. And then if you work in government have loads of money, loads of programs. The European Space Agency was a great employer. They had billions of euros of money to do space research, space station, design rockets, do missions to Mars for ExoMars mission. So you have a lot of resource, but things go slowly. Now you're working in a government. Government is very good at being bureaucratic. So now you've got a bureaucratic environment to navigate, where everything takes ages. It takes 6 months to buy a pencil. You've got to go through committees to buy a pencil for procurement. So absolutely crazy as well. So you've got all of these things, and none of them are perfect. None of them are ideal. But if you're a scientist, you have to navigate all of this and deal with it, and there's pros and cons. But being a scientist in any of those organisations is still better, with all the deficiencies, all the inefficiencies as well. It's still better to be a scientist working in those organisations than not being a scientist and doing nothing. So yeah, it's swings and roundabouts, pros and cons, strikes and gutters. Mm-hmm. Okay.
Anyone else? Or there? Oh.
I really enjoyed a lot your presentation and your talk, and I wanted to ask you, do you have any artistic activities in your history, in your personal?
Yeah.
What is your art?
Well, yeah, I guess I got it from my mum. She was an artist and designer, and she's done hundreds and hundreds of paintings, I think even from galleries and exhibitions. So I get a kind of artistic benefit from that kind of upbringing. And I've done art myself as well, a little bit in school and drawing. Mm-hmm. And I see things very visually in the world. So, I resonate very much to these kind of drawings, because not only are they great science, but they're great pieces of artwork as well, and I don't see much of a distinction there. So I do really appreciate the aesthetic world. And when I go to galleries and museums, and we're going to wander around here afterwards as well, I'd like to see the beauty in the world. So I think there's a lot of beauty in the world, even if it's hidden within a mathematical structure or an equation, or within an anatomical drawing like that, or even in the crystal structure of a tungsten boride material that you've just made. It all just looks beautiful. And that's really important as well, to appreciate the inherent beauty that's inside all of these things. So I appreciate art, and I do my very best, and also with our kids as well. My wife and I, we go to galleries all the time, we go to exhibitions, and you can lose me in El Prado staring at the Garden of Earthly Delights, no problem at all. I could stare at that all day long. I'd have to be dragged away at closing time. So, yeah, no, it's really important. And I think that's a good message for students as well, is to go to galleries, go to museums, go to places like this, because that's where you get this buzz. This is where you pick it up. You know, and that's one of the purposes of a museum like this as well, is to show that inherent beauty that's underlying all of the knowledge that we're accumulating in you know, human culture. So I love it.
Yeah.
Is that a good answer?
Yeah, good, very much.
Okay.
Thank you.
So thank us.
Oh, this could go on all afternoon, I think. Great.
I'm just going to dare my students, our students.
Yeah.
So we will definitely have that in school, right? And I dare them to find pieces from the literature or from philosophy to fit in with all these scientific discoveries. That's a challenge.
That sounds
for you.
like a good project, doesn't it? Yeah, yeah, yeah. And on the website, there's a document called Constellation of Concepts. So you could pick out, let's say, you know, to do with biology, you can pick out the theme of evolution. Now, evolution, that's represented here by Charles Darwin and to a certain extent Alfred Wallace as well, who collaborated with. So that's the picture there showing evolution. But on the website, there are loads and loads of connections to other things where evolution is also relevant. So you can build up, a bit like a star map looking at the sky, you can build up a constellation of these concepts around a single topic. And that topic could be AI, it could be evolution, it could be cryptocurrency, it could be a Mars mission, it could be a new philosophy or an art movement. That's a good challenge to students to think out of the box and then join up the dots using the poster into this constellation map. And there's one example on the website that I've done. There's a few others there as well. But it's when you start doing that, and it doesn't matter what the topic is, and I've done 3D printing and nuclear fusion, it's really exciting. You can actually see how things click together, how to join up the dots.
Thank you very much.
Okay, thank you. Yeah, exactly. Yeah. I'm just going to. I think there were some really good questions today, and I did say at the beginning that there's going to be two winners, and I'm going to go for the question about the deep matter, antimatter physics, and also your questions were really thought-provoking as well. So we have two winners there. If you come up here. You will both now receive your own copy of the Atlas of Human Imagination. No worries. Should we get a photograph? Yeah, come on then.
Well, thank you very much, everyone, for your interesting questions. Thank you very much, David, for such a thought-provoking and inspiring presentation. So we've got plenty to think about over the weekend and going forwards. Okay, all right.
Thank you very much.
Thank you.